Okay, recording is started. So many people still joining. Okay, so now we can start. So good evening, everyone. Myself, Prasil Kapadia, and I will be conducting live interaction session on every Monday from 6 p.m. to 8 p.m. So before, wait, people are joining. Okay, I'll be conducting this live interaction session on every Monday from 6 p.m. to 8 p.m. How many of you attended yesterday's live interaction session? Anyone? Okay. So I don't know how Amit proceeded, but in every lecture, what I will do, first I will be giving you one brief description of what was taught in the last week. Then we will solve some problems using Aspen Plus, and then at the end we will go for some short question answers. So maybe that will help you in assignments. So first of all, before starting anything, I would like to first introduce myself. So, uh, am I audible? Can any one of you please respond?
Yes, sir.
Okay, okay. Thank you. Okay, so before starting, I would like to first introduce myself. So I am Prasil Kapadia. Currently, I am pursuing my PhD from IIT Bombay. Uh, if I talk about my Aspen experience, I have learned Aspen in my BTech from NIT Surat. There we had one course of computer-aided design in chemical engineering in final year. There we learned first Aspen. After that, I joined Reliance Industries Limited at Jamnagar. At that place, I used Aspen for 1 year to increase the design capacity of high purity isobutylene plant and to check the hydraulics of condensate system. After that, I joined IIT Kharagpur for my masters, and there I worked with Professor Amya Kumar Jana. Um, he was my guide. Someone is joining. He was my guide. During my BTech, during our BTech, we learned most of the Aspen from his book only. So I will also follow that to teach you Aspen from that book only. So first of all, before starting the course, can anyone tell why do we need to go for Aspen? Why are we learning this course?
For the modeling and the simulation.
Okay, for the modeling and the simulation, that we can also do without use of any software. Then why are we specifically doing this using a software?
For trial and error
Time
method.
saving.
To
Okay, time
reduce our
saving,
calculations.
reduce our calculations. Nice.
Like
Anyone else?
to design production engineering.
I'm sorry, I couldn't follow you. Can you please repeat? Hello. Okay. First of all, can you please all raise down
When we
your hands?
use software, we can vary our flow rate, the conditions, and get our desired product. And it would help us in simulating the plant with the various constraints and assumptions, whatever we have. And
Okay.
doing by hand, it becomes very difficult.
Okay. So if by doing this and becomes very difficult, can't we write our code to solve the equations, solve the
We
system?
write our code, but in industry, we need some ready-made tools where we can pick unit operations and put our inputs, verified inputs, so that we can get our desired results. And maybe in research we can write our codes, but
Okay.
in industry
Okay.
it becomes very hard
Okay.
Right. Right.
Okay.
to
Good.
kind of
Good. Good.
result.
Okay, good. Okay, one request from to all of you. Can you please raise down your hands? Maximum I can see. Still. Okay. So, okay,
Uh,
more or less what everyone of.
to
Okay,
interrupt
sorry.
you,
Yes,
could you please repeat the name of the book which you are referring for this course?
I will mention at the end. I will mention. Actually, that book is not available in PDF format. I will mention that book at the end. Is that fine?
Okay. Okay, okay, doesn't matter. Okay,
Okay, I will. I
okay.
will.
And
Yes.
one more question I do have that
Yes.
before registering this course, I thought that this is for Aspen HYSYS, but after
Hmm.
registration, I came to know that this is for Aspen
Aspen
Plus.
Plus. Yes.
So uh, I believe there is not very big difference between the user interface and the way we do simulate things in HYSYS and Aspen Plus.
Okay, I'm sorry, but I have not used HYSYS during my job also. I have not used, so I don't have idea. But I guess interface or the concepts that you are understanding, those are more or less same.
Okay.
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 Yes,
Okay.
I
So,
can
Thank you
reply
very
for
much.
this
Thank you very much.
question.
Please continue. Hmm.
sorry, someone is saying something. Can you
I
repeat?
can reply for this comparison between Aspen Plus and Aspen Hyacinth.
We'll go through that. We'll go through that.
I
Russell,
can
can
give
you
the
hear me?
answer.
Sorry.
I can give the answer for comparison of Aspen
Okay.
Hyacinth and Aspen
Okay.
Plus.
Say it.
Yeah, actually, Aspen Hyacinth is mostly for upstream operations that will simulate very well for upstream, and Aspen Plus is using for all the downstream chemicals. But in the sense that if you use Aspen Hyacinth also for the downstream chemical simulations, it will be also very good. But actually, in the inside database, property database, and thermodynamics, mostly both are same. So you can use
Yeah.
any software.
Okay.
Thank you.
Russell,
Uh,
I
Sorry.
have one doubt.
We will go through all the doubts.
No, no, it's a general doubt. So
Okay. Say.
yesterday also I attended the session and
Okay.
the faculty said the slides and the recording would be shared after the session. But can you
Okay.
tell
It is
me
no.
from where
Okay.
I
I
could
don't
access
know. Okay. I don't know how Amit conducted his session, but after my session, I will upload this session on YouTube. So you can, I
and for the
guess, search
slides?
my name. I guess you can search my name and it will be there. I'm not sure, but I will be uploading most probably today itself after session.
Okay, okay, fine.
Okay, guys, let's start. So I don't know how Amit proceeded yesterday, but I'm repeating this for this Monday session that I will be conducting. First, we will be discussing what sir has already taught in the weekly lectures. Then we will go through some problems using Aspen Plus, and then at the end we will go through some short question and answer session that will be useful maybe for your assignment or for your basic understanding. Okay. So as most of you have already told why we use Aspen Plus, I will also repeat. So let's understand this by acetone manufacturing unit. So for this acetone manufacturing unit here that I'm going to discuss, acetone is manufactured from dehydrogenation of isopropanol. So the reaction is like isopropanol gives acetone plus hydrogen gas. Now this is a gas phase reaction that occurs at very high temperature and high pressure. So I guess you can see my mouse cursor. So okay, someone is joining. Okay, so from storage tank, isopropanol is first sent to the reactor. That reactor is tubular reactor, but as I mentioned, the reactor conditions are high temperature, 500 degrees Celsius and 4 to 5 atmospheric pressure. So to meet that requirement, first we send our isopropanol to a heater that heats up our isopropanol, and then someone is not muted. Can you please? So first, we will be heating our isopropanol using a heat exchanger, and then it will be sent to a compressor. So what happens after first we heat our isopropanol using a heat exchanger. So temperature of the stream will increase, and then when we pass it to the compressor, what compressor basically do? Compressor increases the pressure of feed stream. So this isopropanol enters on tubular side of this reactor, and we add some flue gases or heat transfer salts to carry out our reaction. So as I told, from the reaction we get acetone and hydrogen. So this acetone and hydrogen mixture we send for the water scrubbing. Why are we using water scrubbing? Because hydrogen is a lighter gas. So we can easily remove by using a water scrubbing operation. So after water scrubbing operation, we will have some leftover water with our feed stream. This product stream, not feed stream, I should say, from this product stream. So we will have the mixture of isopropanol, unreacted isopropanol, then acetone and water. So now to separate this into our desired acetone product, we go for two distillation column. As of most of you know how distillation column works, it works on the um, difference of boiling points. So iso propanol has boiling point of around 82 degrees Celsius. Water we all know 100 degrees Celsius, and acetone as minus 56 degrees Celsius. So from the first column, we will be getting acetone from the top, and the left mixture of isopropanol and water is obtained. Now to separate that, we are using one another column that separates isopropanol from the top, and that is recycled to our feed stream, and water from the bottom. So this is one example plant that I am taking. So now can anyone tell me, as I told, we need our reactor condition 4 to 5 atmosphere and 500 degrees Celsius. So first we are heating our steam, we are heating our feed stream, and then we are compressing it. Can we do reverse? Can anyone tell? Hello? Can anyone tell, can we first use compressor and then go for heat exchanger?
We can't do that.
Why?
It won't be
Again,
feasible.
Sorry, it won't be.
It won't be thermodynamically feasible, sir.
The energy should be supplied more, like
Yeah,
because
please continue.
we compress, like the pressure and the temperature may vary,
May vary.
which
Okay.
uses much
The
energy.
energy is wasted.
Okay. Anyone else wants to respond?
As we use the pressure first, the energy
Yes.
required is less also.
Energy requirement. I'm
Uh,
sorry, I could not follow you. Can you repeat?
Yeah, the energy requirement will be less because the
If we,
temperature rises.
yeah,
yes, the
temperature rise.
temperature rises because
Then we
as
need a
we increase the pressure.
requirement of design pressure of that heater
Okay,
will be
good.
changed.
So this is one of the reason, and another reason we can also think of compressor. What do we generally feed in compressor? Is it gas or is it liquid?
is
Yes,
Gas,
gas,
always
Yeah.
gas.
gas,
So
without a trace of liquid.
yeah, so we need to increase our feed temperature in such a way that what compressor do it reduces, it increases pressure and it reduces temperature to some extent. So what if during our process, vapor is converted into liquid? So that is not desirable for our compressor. So that is also one of the reason why we first go for heat exchanger and then we go for compressor. Okay, is this clear to everyone?
Yes.
can you repeat, sir?
Could
See.
you please repeat again?
Yes, compressor we need feed as vapor, right? But from upstream, the isopropanol that we are providing, if the temperature is not considerably high or the isopropanol is not in a good vapor form, then during compressing process it can condense in good amount, and cause that can cause problems like corrosion and damage that can damage to compressor. That is also one of the reason. That thermal efficiency that most of you told, that is also correct. That is the main reason, and this is also one of the reason. Okay, now uh, let's see what equipments we are using in this manufacturing unit. So one is heat exchanger, we can see here. Then we are using compressor. Then there is one reactor. There is one scrubbing unit, and there are two distillation columns, plus there is one storage unit. So equipments are first heat exchanger. What does heat exchanger do? Say someone.
It
Gives
it could increase
gives
or
the
reduce
desired
temperature.
temperature.
It increase the
It could either increase or reduce temperature.
how does it do that? Increase or reduce the temperature? By using some external, like say steam, if we
Yeah.
are providing.
Utilities.
Either a cooling medium or a heating medium using.
Yes, heating medium or a cooling medium. Now, then we had a compressor, and we can also have pump. So, can anyone say, can anyone tell me what is the basic difference between pump and compressor? When to use pump and when to use compressor? Basic.
Pump
Compressors
is
Is
are
usually
used for
used for
gases.
liquid.
One by one, please one by one.
Pump is usually
The
used
pumps
for
are used for
liquids.
liquids and compressors are
Compressors.
used for gases, sir.
Yes, yes, okay. So both they are called pressure changers, pressure changing equipments, pumps and compressors. Now then absorber. Absorber is used for to remove impurities from gases, correct? And we add some like in ONGC there is one unit of we are using monoethanol amine to absorb CO2. That is one example of absorption unit. Then reactor. Reactor, we all know we use reactor to perform our main reaction. So what are the various types of reactors?
gas type,
CSTR, plug
CSTR,
flow.
Plug
There are
VFR.
flows,
mainly two types.
mainly two types. Who say it is mainly two types? What's the
There are
name?
Batch
various also types.
Batch and continuous, sir.
is continuous.
Okay, batch continuous. We can have packed bed reactors. We can have continuous stir tank reactors. We can have plug flow reactors. Okay, so there are various kinds of, and here in this example, it was a tubular reactor. Now, distillation units. Distillation units are the heart of any chemical engineering plant. Why distillation is so important? Not distillation, because it is a separation method. We want something after reaction, there are hundreds of things. Those are in our product stream. So we need to separate from those mixture. We need to separate something that is useful to us, that is valuable for us. So that's why in most of the chemical plants, you will find distillation units, and those two with very small height to very large heights. Then storage tanks. Storage tanks, what is the use of storage tank? To store the products or to store our reactants. After the after our reaction is performed, after separation is done, we need to store our product at some place and then we transport that product. So at one place we need to store that. So for that storage tanks are used. There are also various kind of storage tanks. And mixer and splitter. What mixer do? Mixer mixes one or two streams or three streams. And if let's say for some reaction we need the mixer of two reactants. So for that we can use mixer or splitter to split the streams. Okay, so these are various kinds of equations, various kinds of equipments that we can see in any chemical engineering plant. Just a minute, someone is waiting. Okay, so from all these units, let's just talk about first distillation unit. So on any tray of distillation unit, this is the total material balance. Ln plus 1 plus Vn plus 1. L is liquid flow rate, V is vapor flow rate. So n plus 1 is it is entering from n plus 1th tray. So V n plus 1 or it n plus 1 plus V n L n plus 1 plus V n minus 1 liquid is entering from top, vapor is entering from bottom, minus Ln minus Vn. Those both are leaving. So this is overall material balance on each tray. I'm writing on each tray. So let's say there is one feed stream. Let's say I am on fifth tray and there is one feed at fifth tray. So we will just add our plus F to that particular tree. Now, if we talk about component material balance, how can we write component material balance? We just multiply that particular flow rate with particular liquid or vapor composition on that particular stage. Then energy balance. Energy balance also similarly we need to work with liquid and vapor enthalpy for respective liquid and vapor streams. Then we need to know equilibrium relation. This is nothing but Raoult's law. We will discuss that. That is yp equal to x gamma p set. So to know the composition of y on each tray, we need to solve this y equal to gamma p by p set by p into x. So p set is basically temperature dependent, and gamma, those are very gamma is activity coefficient, and there are various activity coefficient model available. We will discuss that. And at the end, this summation rule must be followed. Summation of x equal to 1 and summation of y equal to 1 on each tray. So let's not currently worry about this dm by dt part, that is unsteady state part, and that is nothing but a liquid holdup on each tray. So let's not worry about that currently. So let's imagine, just imagine, you have a distillation column with 30 number of trays. So how many total material balance equation you will have? 30 equations, correct? Then let's say you are separating benzene, toluene, xylene, three components. So you will have 30 into 3 on each tray, three component balance. You can go for two because summation of x is 1. But let's consider there are three equations on each tray, three components on each tray. So three equations on each tray. So there are total 90 component mole balance equation. Then similarly 30 energy balance equation. So how many equations we will have? We will have around 150 equations, correct? So is it desirable to solve these 150 equations on pen and paper simultaneously? That too not independently, simultaneously.
Not feasible.
Not feasible. Let's say you are operating this unit, acetone manufacturing unit. Your plant manager told you that you need to increase the feed flow rate. You need to check to meet some market requirement. We are going to increase our acetone purity. So how will we do that? We will have to play with some feed flow rate. We'll have to play with reflux ratio in distillation column. Then we may have to increase reboiler duty. So there are options and plant is already there. So can we just increase, let's say my feed flow rate is 100 and now I want to operate my plant at 130, 150. Can we do that?
Yes, very
I'm
well. We
sorry.
can increase the flow rate.
I'm sorry, I can't listen to you. Can you repeat?
We can increase the flow rate.
No,
We
I
can
And
increase, but we need to check the limit.
Yes, in plant there are 100 connections. Let's say isopropanol is also coming from some downstream unit. Acetone is going to some isopropanol is coming from some upstream unit and acetone is going to some downstream unit. Can we just increase our feed flow rate and can we just do it? No, we can't do it because plants are also designed at some particular capacity. You can't go beyond that capacity. Okay, so in plant, one of you already mentioned we can't solve now 150 equations simultaneously, and at that time we can check what is going to happen. Is it going to affect my acetone purity or not? We can't do that. It is not practical. It is not practically feasible solution. Correct? So there is a need that we must have something that we can directly see the effect of some feed flow rate, reflux ratio or something. We can directly do that without implementing that part in real plant. Okay, so that's why we are learning Aspen. I hope motivation is clear to everyone. Why are we first learning this software? So Aspen is nothing but the full form. How many of you already knew the full form of Aspen before this slide?
Yes.
Okay, good. So Aspen is advanced system for process engineering and it was developed during 1970s as at MIT. So this Aspen software was basically at initially it was developed to solve some nonlinear equations, series of nonlinear equations. But after that it was now we have many Aspen products available. So we can simulate large processes with a high degree of accuracy using Aspen. Guys, please next time join on time. Okay, so first let's talk about Aspen Plus. So Aspen Plus is basically used for steady state simulations of chemicals. The equation that I mentioned in distillation column equation, those were unsteady state equation because there was a term of dm by dt involved in there. So that actually gives us time evolution, how our product quality, everything is changing with time. So this Aspen Plus that is steady state simulation. Aspen Dynamics that is used for dynamic study. Then Aspen HYSYS. HYSYS is basically used for particularly that is used for oil and gas processing applications. It is also similar, but it is mainly used for these oil and gas processing applications. And that this batch CAD that is used for batch processing. There are so many Aspen tools available, but I have shown some only four here. So how does Aspen Plus works? So Aspen Plus works on sequential modular approach. What is sequential modular approach? Can someone tell me? I guess sir has discussed.
It solves equations unit by unit, block by block.
Yeah, it solves equation unit by unit, block by block. So tell me, okay, first let me open this. Let's say I am solving this unit, this reactor. So it will only solve this block. So how will it consider this recycle stream? Because we are going from here to here to here to here. Then from here we are getting recycle and we are giving back to the reactor these isopropylene. Then how will it work for recycle stream? Because we don't know how much it's going to how much isopropanol we are going to get. Anyone? It's a sequential modular approach that is correct. What it will take, it will guess some initial value and it will iterate the process. It will it will have iterative solution and the solution whatever that converge from here to here that is our recycle stream. So it will start with some maybe random values. Now, I'm sorry, I'm here. Okay, so what can we do with Aspen Plus if we have Aspen Plus? Say you are in a plant and you are told use this Aspen Plus. What can you do with Aspen Plus? What can you think of doing with Aspen Plus in a particular plant? Let's say with that acetone manufacturing unit, what can you think of doing? Hello, someone please respond. I'm sorry, you are not audible.
Can choose the head for the
Sorry.
compressor and flow rate.
We can, I'm sorry, can you repeat please? We can,
Can find out the head flow
Optimize the
and
plant.
flow rate and power consumption of particular equipment source or the heat
okay,
transfer area. We can find out by Aspen Plus and all in steady
okay,
state simulation versions. In HYSYS, it's a bit complex.
okay. Someone told optimization of plant. That is best example. We can optimize the plant. Other than that,
Sensitivity analysis.
yeah, sensitivity analysis. What we can see the effect of one parameter on other parameter. Like we can see the effect of feed flow rate by keeping everything constant on product purity. Then we can see the effect of reflux ratio, keeping everything else constant on product purity. We can increase reheat reboiler heat duty, and we can see the effect. Correct. So it allows various configurations. We can arrange equipments in various configurations. Then it reduced times less effort in new plant design. Let's say I want to design a new plant, but I don't want to set up it first. I want to check if what I am thinking will it work or not. So we can directly design our new plant. Then we can perform what if analysis. That is exactly what someone told, sensitivity analysis. We can see the effect of one parameter on product purity. We can see individually effect of all other parameters on our product quality. We can optimize our plant. What is optimization? Someone told me optimization. So tell me what is optimization?
Best utilization of resources.
Best
Finding the
utilization.
best
Cost is
condition.
reduced.
Okay, best
Total cost is
utilization of
minimum.
resources. Good. Good. So we can optimize our plant because no one is doing charity. Everything is about money. So at what minimum cost we can maximize our product purity? There is one. Okay. Then we can perform debottlenecking. What is debottlenecking? Let's say in plant, uh, in any plant, let's say there are some product quality is the issue and no one is able to find out from their plant, from that actual real plant. So we can perform various analysis and we can debottleneck what is the issue. I guess it's fine for everyone, right? Should I move
Yes,
ahead?
sir.
So debottlenecking means solving a problem related plant, or,
Yes, yes,
or troubleshooting is identifying problem. Yes, it's
yes. Okay, when I was in
okay. So
Reliance, okay, I will share a little story. I was in Reliance. There was a plant, I don't remember the name of the plant. So what was happening? Uh, they were they were entering their feed at some particular tray number. So what was happening? That was not giving maximum product quality. So what they did, they perform this analysis that what can we do, what is the issue and how can we solve that. So they just change the various feed tray location and increase the product purity by seeing that on not on the, let's say, tray number 5, on tray number 10, if we enter our feed at tray number 10, then it will increase our product purity. So if there are these issues, like plant is already designed, maybe those errors are because of some person who designed the plant, we can also rectify those errors. Okay, again someone. Guys, please next time onwards join on time. Okay,
One
so
more
now,
comment on debottlenecking.
okay,
So actually, debottlenecking, in addition to your explanation, debottlenecking also we use for increasing the plant capacity. Okay, we want to increase
yes,
from current capacity to the new capacity, so
yes,
that
yes,
we need to see where is the bottlenecks in the equipment, so that
yes,
we can add additional equipment or design a new equipment more than its capacity,
yes,
so that
yes,
so we can use debottlenecking exactly in these places. And troubleshooting is the identifying the existing problems, like
yes,
currently
existing
some leaks are
problem.
there but you are not getting the exact temperature from the
Yes,
reactor. What's happening? Maybe inside tray collapsed or something like that. So we can identify using troubleshooting. So this is the
yes,
difference between debottlenecking and
yes, correct,
troubleshooting.
correct, correct. Okay, so let's get started with Aspen Plus. Uh, okay, first let me check. How many of you are having access to Aspen, or how many of you have downloaded Aspen on your personal computer or somewhere? Okay, I guess there are good number of students. We can also solve some
They're
good problems today. Sorry,
asking for the license. I was having
I'm
trouble
sorry,
with
you
the
are not
license
audible.
something. So am I
Okay, I
audible?
guess yes, you are audible. You have issues with your license. So actually with license part, I can't help you. You need to mail, I guess, sir or some team member from NPTEL, because I'm not using IIT Guwahati's license. I'm using my IIT Bombay's license. So I don't exactly know what will be the issue with your license.
Okay, sir.
Okay, but how many of you? Only 9 students have access to Aspen. That's a very small number actually.
I have.
Okay, 11 students. So you can currently use Aspen in your laptop if I give you some problem. Can you do that? Don't worry, I will not, but I'm just asking.
Yes, yes.
Okay. So let's first get started with Aspen. So when you open Aspen, this is the window that you saw. I'm sorry. You are not audible. Can you repeat or can you type in chat box?
Aspen plus, Aspen 1 or Aspen HYSIS.
Aspen Plus. Aspen Plus. This course is all about Aspen Plus. It is not about Aspen HYSIS. So I will be, or Amit also, anyone of we will be discussing only Aspen Plus, not Aspen HYSIS. Okay, so this is the window it looks like. When we go for open is generally used to open some existing problems like this. I have already solved problem 1, problem 3, and we will go for new simulations. So for new simulations, there are some batch process, gas processings, mining and minerals, refinery. Those templates you can directly use. We will not be going for those part currently. We will be just going for new simulation. So if we go for new simulation, it will open. You'll have to bear a bit with my internet connection or laptop. Which version is provided to you, all of you? Is it 14 or some other version?
Aspen 12.1.
Okay, you guys are provided with 12. Okay, this one is 14. I have 14. Okay, so first, when you open the window, you have this properties tab, simulation tab, safety analysis and energy analysis. Currently, it's not important for us. Currently, it's not important for us. Then in the top screen, this one is for units. These are English units. This is metric unit with Celsius and bar and SI unit. So English units, pressure is in PSIA, mass flow is pound per hour, mole flow is pound moles per hour, enthalpy is British thermal unit per hour, and volume flow is cubic feet per hour. So according to our requirement, we can choose units or we can later also we can change it. So this is about units. Then analysis part we will do today. So I will show it to you. Then, okay, let's go for this component, how to add a component. So first go to find. Let's say I want to add first benzene. So what will I write? Benzene. Benzene. I will click find now. So there are so many options available. If you can see here, begins with, contains and equals. So I have chosen contains. So all components, those have benzene in their names. It will be shown here. If I go for equals, so it will, I guess, only show benzene. Someone is, yeah, it will only, yeah, it will only show benzene. So it is up to your requirement. Then we can also search our compounds based on molecular weight. Let's say I want to search from 60, benzene has molecular weight of 78. So let's say I want to search from 60 to 110. And let's see what it gives. So it only gives benzene from in this database, only benzene is having 78.11 molecular weight. Okay, I have chosen contain. If I go for contains, it will only show with 60 to 110. I guess this will be a huge list because we have chosen contains. Someone is joining. Guys, please join on time from next session onwards. Okay, I guess it's okay, I'll close this currently. So we can add a component. Let's say I'm currently going for benzene only. I'm typing benzene. Fine now. Then I will add this component. Okay. Now, let's say if I want to change the name here, this is the component ID. This component ID will, this name will be reflected in your stream results. Like if you have given this benz01, it will show like benz01. So we can change this name from benz01 to benzene. And what is the limit? How many characters can we add? Anyone?
8 characters.
Yeah, 8 characters. Up to 8 characters we can add. Let's say I'm trying to write benzene 1, 2. I can't go ahead. It won't allow me. Okay, so just benzene. Okay, one more thing I want to show. So these are the data banks from where the properties are chosen, properties are selected, and you can also search from your PubChem. Like say I want to search mcrisol, so it will appear here. Yeah, all components containing mcrisol, it will appear. Okay, so this is how you can add components. So components can be added based on the name, plus if you know the molecular weight range or if you know the boiling point of the component. So you can add component like this. Now, okay, I have already added benzene. Okay, now I want to move ahead. So just click on next button. This is the next button and with arrow. So here, this is the section for methods specification. Why do we need this section method specification? Can anyone tell?
To estimate the properties, maybe thermodynamic or chemical properties, physical properties.
Okay, so from this section, we can add methods like say I want to simulate my whatever block using NRTL equation of state. So I will use NRTL. What is NRTL? NRTL is non-random to liquid theory. Then if someone wants to, it's a gas-phase reaction, someone wants to go for SRK equation of state, or let's say VTPR. VTPR is nothing but volume translated Pang-Robinson equation of state, some liquid activity coefficient model, UNIFAC or UNIQUAC, picture correlation. So we can choose these models from here. So this depends on which kind of system you are working with. So we will see with this example, with one example, where we are using ideal system. So what is ideal system? That basically follows ideal Raoult's law. We'll see this. So I'm just adding this. Currently, it's not important. Okay, one more question I have. In petroleum calculation options here, you can see it is free water method. What is free water method? Can someone tell me? It's not use. It will not be useful for us currently because it is for mainly petroleum products. But if it's already there, can anyone tell me what is free water method?
If we have water as a chemical component,
Sorry, I couldn't follow you.
if we have water as one of the chemical component,
No. Okay, I will tell you. In oil and processing units, we get two phases like water phase and oil phase. So what happens? Water is also soluble in oil phase. So that if we are considering that solubility, if solubility is very low, we are safe. But if we don't want to consider that water is soluble in oil, so our calculation load will reduce. So that is basically free water method. It does not take account that solubility of water in other oil phase. So it's not important for us. So don't worry about it. Now let's go for next. So here, this is our simulation window, how this simulation window looks. So currently there is one rate symbol, flow sheet not completed. So we have not added anything, so we can't run anything. So this symbol, this red half red symbol that shows that something is missing. It's not completed. So let's start with mixer. Mixer, I already discussed. We want to mix streams. Then F splitter and S splitter. If any of you have already followed second week lecture, can tell me what is the difference between F splitter and S splitter? Does anyone have watched second week lecture? Okay, no. Let's leave it for now. Then we will discuss this on next week. There are two kinds of splitter. Now separators. We will be discussing. We will be simulating flash drum today. So there are various kinds of flash drums available. One is flash 2 that is basically used for separating. It performs rigorous vapor liquid equilibrium calculation. Let's say two. I have a stream benzene plus some water, benzene plus toluene. So I want to use a flash. I can use flash 2 drum because I can have one liquid phase and one vapor phase, and I can go for flash 3 if I want to see. I want to consider two liquid phases and one vapor phase. Then decanter we all know decanter separates product based on density difference. So if I want to separate oil and water, what will happen? Water will be at top or bottom?
At bottom.
Bottom.
Then we'll go for exchangers. Sorry.
Bottom.
Okay, now we'll go for exchangers. So someone is saying something. I guess no. Okay, now we'll go for exchangers. So exchanger, someone already told in slide 2 that heat exchanger is used to transfer heat from processing. So there are various kind of heat exchanger. This is simply heater. This is heat X. Heat X generally takes cell and tube heat exchanger where two stream co-current or counter current. This heat exchanger design we will see in next Monday's session. Then these are multiple heat exchangers. So what multi M heat X takes? It takes various. Let's say I want to heat up three streams using two streams. Like say I want to heat up benzene, toluene, xylene using two water and something else. So for those kind of condition, we can use this multi-stream heat exchanger. Then this HX flux is basically used to estimate LMTD. This also we will take example next week. Sir has already covered this in week 2 lecture. So we will leave this for next week. Now for columns there are also various kinds of column. These are distillation columns. So this first is DSTWU that works on a shortcut. This is a shortcut designing method of distillation column that works on Underwood Gilliland method. We will see all these equipments. We will see mixer splitters, exchangers, and columns in next class. So I'm just giving you the overview. Then red flag column that uses rigorous criteria that just doesn't use this shortcut method. It actually performs all kinds of calculations to estimate the values of product quality, reflux ratio, and all. Then next is extraction unit. So extraction unit is, let's say I want to perform a liquid extraction. Let's say I want to remove levulinic acid from water using some solvent. So for those kind of application, we can use this extraction unit. Does anyone know how to remove this admitting option?
Are
Anyone
you
can
audible?
directly can.
Am I audible?
Yes, is you're
Hello.
audible.
Sure. In Aspen 12.1, we don't have columns by some. I don't know why, but we don't have it in our function.
No, columns
Maybe
must
it's
be there. Column was even in 8 Aspen version 8 when I used it.
no, sir. We have controls one, controls two, pressure relief, mixer and splitter, separators. So is separators in columns over? No. Then we have heat exchangers, reactors, pressure changers, manipulator, polymer models, and model chest. That's it.
Okay, let's take when we are going for example. I will see what is the issue. You can
Okay.
share your screen at that time.
No,
Okay.
you can
Thank you.
try and reopen the application. I am using same 12.1. I have columns in my
Yes, Aspen
software.
has. I have used Aspen version 8 some years ago and it was already there. So columns, they can't remove columns. It must be there. Okay, then next these are reactors. So reactors we will not be simulating reactors for now. It may be take week 3, week 4 or so on. At that time we'll go for reactors. So generally CSTR, continuous stirred tank reactor, plug flow reactor, batch reactor, and these are some stoichiometric and based on yield. This we will see when we will be performing reactor calculations. Then we have pressure changes. So pump and compressor, I have already told you, pump is used for liquids mainly and compressor is used for vapor. Then these are multiple compressor in series. Then valves you can go for control valve application, what should be the opening percentage opening we should keep of a control valve. Then there are pipelines. Pipelines are generally used for hydraulic studies. So I don't think pipelines will be using for now. And these other options, it won't be useful for us. These are mainly for solid operations and we will not be, I guess it won't be covered. And if it covered, we will see how to do that. Okay. So, okay, we'll take some example now. Units
Sir,
we
can you?
already,
Hello.
yes.
Sir, you can that you need to admit all means all participants. So you can remove the go in setting and remove that option.
Okay, I'll keep this for next time. I don't know how to do that. I'll keep this for next time. But everyone should join by 6. If it's the time is 6, everyone should join by 6 or 6:15, not at 7. I will figure out how to do it. Okay. So now units we have already discussed. Now equation of state, those I was talking about, Van der Waals equation of state, RK equation of state, SRK equation of state, PR equation of state for gas phase. So these equations, I'm sure all of you must have learned these in your chemical engineering thermodynamics. How many of you have performed the calculations to estimate volume of liquid and vapor on pen and paper? Most of you may have, I guess. It is in Smith, Varnes and Abbott book, and it is painful process. Most of you know. In Aspen, it takes these parameters in some different way, but the basic concept of this all equation of state is this only. Then, okay, let's start with Rolle's law. So, in a closed system, liquid and vapor with temperature T and P are in equilibrium with composition Xi and Yi. So, for Raoult's law, I am talking about ideal Raoult's law. So, ideal Raoult's law, it assumes that vapor phase is in its ideal state. So, when can we say that vapor phase is in ideal state? 2 points. I guess everyone know when interaction between molecule is negligible and volume of gas is negligible to box. Volume of molecule is compared volume of molecule is negligible compared to the volume of box. So in this case, we can consider vapor phase as ideal. So generally, we consider ideality in vapor phase as low temperature, high pressure. It behaves ideally, so we don't need to worry about ideality about vapor phase. But main problem is ideality in liquid phase. So in Raoult's law, we assume that liquid phase is also ideal. So can anyone tell the properties of ideal solution when we can consider the solution is ideal? One by
Sir,
one,
when the
one by one,
sir,
one by one.
sir, we can consider the solution is ideal when the pressure is very low and the temperature is very high, so
No.
that the intermolecular interactions is purely elastic, sir.
Okay. I'm sorry. Someone, can you please just remove this video sharing or screen sharing? It's showing here. Okay. Any other points about when can we consider liquid phase as ideal? There are so many points, not just this one, that interaction.
When the
Anyone?
molecules in liquid
Then what?
are of same size.
Yeah, molecules in liquid phase are in same size. Then one more important part we are missing.
Volume of
Uh,
mixing is
I-
negligible.
if I may, if
Volume
I'm
of
not
mixing
wrong,
is
zero.
negligible. Yes.
If it
And
has zero
one more.
viscosity.
Sorry.
When there is no interaction between molecules.
Yes, there is no interaction between molecules. There is no volume change upon mixing. Then one more important thing we are missing. When we are mixing up two solutions, it should not release or absorb any amount of heat upon mixing. So delta heat of mixing should be 0. So by these assumptions, we can use Raoult's law. So Raoult's law is given by Y into P, that is equal to X into P set. But we know the reality. gases may behave ideally, but liquid solutions, they don't behave ideally. If we take the example of ethanol water, do delta V mixing is zero? If we mix ethanol in water, will it be the
No,
same size? Volume will
No.
be same?
no,
No,
it
it
may
won't be
it may
same.
change.
Volume will change. So, sorry.
It may change
Yeah, it may no,
when we
it
are
will
mixing.
change. For ethanol water, it will change. So for this kind of condition, when you are not having ideality, so you need to use modified Raoult's law, that is given by y into p into phi is equal to x gamma into p set. So gamma is basically activity coefficient. So activity coefficient is that measures non-ideality in liquid phase, and phi is fugacity coefficient that measures non-ideality vapor phase. So generally, in our most of the studies, our operations are at low temperature, low pressure, high temperature. So in most of the cases, we consider phi to be 1, but activity coefficient, we can't consider it to be 1. So what can be the values of activity coefficient? It can be greater than 1 or less than 1. So when can it be greater than 1? Someone
Positive
wants to
deviation from ideal.
okay, positive deviation from ideal case, ideal behavior. So what does that positive deviation means? What does that positive deviation means? This is correct, positive deviation.
Volume is increases. If
Repulsion,
some of the volume is increased.
those are repulsive interactions. So what will happen? This will push component toward vapor phase. So let's say if you are having a solution that has gamma is greater than 1. So what I told, repulsive interactions, and this will push component towards vapor phase. So what will happen? It will easily boil, right? So that is called minimum boiling mixture. Sorry, someone is again trying to join. I need to figure this out for next time. Okay, so we will be working with Rawl's law for today's session. And there is one example with Wilson equation also that we will see when it comes. So first, we'll be seeing the flash drum. So flash drum is nothing but a single stage separation technique in which vapor stream is enriched with more volatile components and liquid stream is enriched with less volatile components. So how flashing operation is performed? We reduce the pressure of the feed stream or we increase the temperature of the feed stream. This we will see through one example, through three examples actually, not one. So this is the flash drum. We are feeding something with F flow rate and V and L, vapor and liquid, we are obtaining something, and this Q is the heat duty that we need to provide. So these are the equations. Sir has already discussed this, so I will not go for equation part, but that is nothing but F equal to L plus V, that is component balance, then FXF equal to LXL plus VYV, that is individual component balance, then this is small, this is Raoult's law, K equal to P set by P equal to Y by X. Here you can't see any phi term or any gamma term, so this is ideal Raoult's law. Then Q is heat duty is nothing but heat released minus heat of vapor plus liquid stream minus heat of feed stream. So that is the heat duty that we need to provide, and that heat can be calculated using MCP delta T. That is, this is nothing but MCP delta T. F into XF is particular flow rate of that particular component, CP of that heat capacity of that particular component, and delta T temperature difference. So let's start this example of flash drum. Okay, in flash drum, first, let's see what is the question. A liquid mixture consisting of 60 mole% of benzene and 40 mole% of toluene is fed with a flow rate of 100 kilomole per hour at 3 bar and 25 degrees Celsius to a flash chamber. We are using flash because we have two components, benzene and toluene, and it is operated at 1.2 atmospheric pressure and 100 degrees Celsius. Here we have increased the temperature of stream. So applying ideal property method, calculate the amounts of liquid and vapor products. Okay, I will show you how to solve this. So first, we will add our components. We have benzene and yes, we have benzene and toluene. So benzene I have already added. We will be adding now toluene. Okay, I will go for equals. There are so many options available. Yeah, toluene. Add. Correct. So I have added benzene and toluene. I will rename it as toluene. Toluene. Rename it. Okay. Now just use this next button. So it will automatically. Okay, first we need to change the property method. Actually, I have already specification is what we are using. We are using ideal. So ideal is nothing but ideal property method use Rawls law and Henry's law. So this is correct. Now we will go for simulation. So we will prepare our setup. So in separator, first we will add flash is a separation unit. So from separators part we can add flash 2. So here I am adding flash 2. Now what I want to do, I want to flash 2 is 1 feet stream and it will give one liquid stream and one vapor stream. So by using this material option, we can add stream. So whatever you are seeing as red, that you are supposed to give. Without that, you can't move ahead. So we are giving feed stream. We are giving, okay, it's an issue. I can delete it also, or I can reconnect to source. Okay, and this is bottoms. Okay, so I will change the names feed, F, then top and bottom. Okay, and I will change the name to flash. You can do it. You can skip this. It is up to you. Now we can either choose to this F stream and it will navigate us to enter the feed specification, or we can just directly go to next. Okay, we are going to next, and this is F material input stream. So what is the temperature given to us? Feed temperature is 25 degrees Celsius and pressure is 3 bar. So let's add 25 degrees Celsius. Unit you need to check and 3 bar. If you want to change the unit, you can change it from here. Then flow rate is given, I guess, 100 kilomoles per hour. So 100 kilomoles per hour. Now 60 mole percent benzene and 40 mole percent toluene. So from here, I will add mole fraction 60 benzene, 40 toluene. If you don't give 0.4 toluene, I guess it will automatically take 1 minus 0.6 because this has turned to this means that input required. We have fulfilled our input requirement for this particular section. I will add 0.4. Now we can go to next. Okay, here this is flash 2. So here we need to add flash condition. So what is the flash condition that we are having? We have 1.2 atmospheric pressure and 100 degree Celsius. So here 100 degree Celsius and 1.2. Now I have to change it to atmospheric. Okay, wait, it's not happening. Atmospheric. Okay, there are many options like we can provide heat duty, we can provide vapor fraction. We will see how we can what we can do with vapor fraction. Okay, now see here required input complete. So now we can run our simulation. So I will just press run. It's taking time. Okay, so here we can see that results are available. Let's go to result summary and yes, result summary and streams. Okay, so from this, let's go for just mole fraction part right now. So feed had 0.6 and 0.4 bottoms. What is more volatile, benzene or toluene? Obviously benzene because toluene is yeah, because toluene has one CH3 ring, so it will not vaporize easily. So first Benzene we will obtain from top and toluene we will obtain from bottom. So these are the mole fractions that we are getting. Benzene as 0.66 and toluene as 0.55. So what we can check here, we can check our material balance. F should be equal to B bottoms plus top flow rate. That must happen, else it won't run. You can check this by your own. Okay, so this is the example of flash drum. Okay, is anyone having any query? Okay, I guess the answer is no.
So this is the optimized solution or just a solution?
No, this is not optimized solution. This is just the solution. Okay. Uh, uh, Now I want you, at least for those who are having Aspen, I want you to try this example. I will also show how to solve it, but for now I want you to try. So what is written? A liquid mixture consisting of 60 mole percent benzene, 30 mole percent toluene, and 10 mole percent of xylene. It is flashed at 1 atmospheric pressure and 110 degrees Celsius. The feed mixture with a flow rate of 100 kilomole per hour, that is our feed flow rate, that enters the flash drum at 1 atmospheric pressure and 80 degrees Celsius. So using the ideal property method, compute the amount of liquid and vapor. Okay, so can anyone tell what will happen? We have feed condition at 1 atmospheric pressure and 100 degrees Celsius. And our flash is operating at 1 atmospheric pressure and 80 degrees Celsius. So what will happen? Will it work? Hello, anyone? Please respond.
No, the temperature should be
Our
more.
Temperature should be
our
more. So
pressure should
We have to cool
temperature
the
or pressure
temperature,
should,
reduce the, sorry,
yes,
we have to reduce the temperature to run
yes,
the reaction.
yes. So can you guys start simulating it? I will also show, but I want you to try by your own.
yes.
At least for those who are having their having Aspen in their PC. Okay, I will just do just first complete the part A, then we will discuss part B. Or does anyone want to share their screen and show everyone how to solve it? That is also fine for me.
That's the good thing.
Okay, who wants to
Anyone
volunteer?
can share your
Who
window.
wants to volunteer?
Can, can I share?
Okay, you do it. I will stop sharing my screen. Now you do it.
Xylene, which xylene we should add?
Go for orthoxylene. Yeah, it's orthoxylene. In question also it's orthoxylene. Okay, I can't see your screen. Whoever was saying to share. Yeah,
Is it visible?
it's visible. Yes, it's
Yeah,
visible. Okay, so you have added benzene, toluene, and you want to add one more component that is orthoxylene. Is there issue with your laptop or something else we can't see? Abhijit?
Yes. Uh,
Yeah,
I have
okay, it's
shared.
showing. Yeah, it's showing now. It's showing. Okay. Now
We have
see,
a
he has added all three components, benzene, toluene, and xylene. Now what he needs to add? He will add property method. So just press next. Okay, so what is the property method that we are supposed to use? Xylene. Okay, for benzene toluene, we are using ideal property method. Is this valid if we go for ideal property method?
sorry for the interruption.
Yes,
How we can choose our method, property method for
yes.
for a particular process.
Yes. No,
Or we
I'm
can
just talking about this benzene toluene. For benzene toluene, is it valid to use ideal Raoult's law? Y into P equal to X gamma P set,
Yes,
where we are taking gamma. Why?
I'm just generally
sir,
asking.
because the benzene and toluene has
Yeah, you're
similar
correct. You're
molecular weight.
correct. I am not saying you're wrong. You're correct. Yeah, you're also correct, whoever responded.
It's a
Benzene
closed
and
compound.
toluene.
Yeah.
Yes, yes. That's why we can use ideal. Okay,
For
now
xylene, we
please.
can also use it.
Yes. Up to some extent, we can go for it because those are similar molecules, benzene, toluene, and xylene. Okay, now go to next. Or directly go to that simulation window. Yeah, you can directly go there and add flash drum. Okay, you added flash drum. Then materials. It's a bit lagging, I guess. Is it for everyone or is it just for me?
For all, for all,
Okay, okay.
Yes, it's lagging.
there is some slow.
Now go to next and add feed composition. I'll tell you what is the feed composition. We have 60 mole percent benzene, 30 mole percent toluene, and 10 mole percent xylene. Don't forget to change composition from mole flow to mole fraction. It will create a huge mess. These are small mistakes that we have also done during our time when we were learning.
What is toluene?
60, 30, 10. 30% toluene and 10% xylene. Then 1 atmospheric pressure and 110 degrees Celsius.
80 degrees Celsius, right?
110, 110 degrees Celsius and 1 atmospheric pressure.
No, in problem statement, flash drum was at 110
It
and
is
the
it is
feed
a
temperature
flash
was 80
condition.
degrees.
I'm
Flash
sorry.
flash condition.
Flash condition 80 degrees Celsius and 1 atmospheric pressure. Feed flow rate is 100 kilomoles per hour. Right, 100. Then go to next. It will.
No, feed was
Right.
at 80 degrees, right?
No, feed is at 110 degrees Celsius and flash drum is at 80 degrees Celsius. Okay, I guess we have written. Now just you can see required input complete. So you can run it. Just run it and see what happens.
Processing input specification.
Yeah, it will take a bit time.
Generating results.
Yeah, results available. Go to result summary, this option, yes. And streams. Okay, is anything happening? Nothing is happening, right?
Yes, nothing is happening. Vapor is zero
Nothing
zero
is
zero.
happening. Yes. So we can't simulate it because either we need to increase the temperature or we need to provide some heat duty. So what was the part
I'm
B?
not
In
able
part
to see
B,
the screen.
sorry, hello,
I'm not able to see the screen.
whose screen? Abhijit's screen. It is visible to us. Okay. In part B, what was told, repeat the calculation at 1.5 atmospheric pressure and 120 degrees Celsius. Can you do that? Now change the flash drum condition, go to flash and change that conditions. Yeah, go to blocks. Or you can just add from main flow sheet also. Just click on that block. Yeah. The temperature is 120 degrees Celsius, I guess. Just a minute. Yeah, 120 degrees Celsius and 1.5 atmospheric pressure. Okay. Okay. One advice I want to give. Wait. Okay, you have already simulated it. Okay, let it happen. So when you are doing, let's what we did first, we simulated a flash drum at 180 degrees Celsius and 1 atmospheric pressure. Then you change the input, right? In flash drum. So always go for reset option and then run it. This is my from my personal experience. Don't just run directly. Reset every calculations and then again run it. Sometimes it happens that it gives some garbage value. I had some experience, that's why I'm telling it. It may not happen
Means
here. Reset option next. You can see the next option, right? There only there is reset option, last option.
Hello.
Yes.
Hello, sir. Am I audible?
Yes, you are audible.
Sir, actually, I install the software, but
Okay.
can I show my screen?
Okay, no, regarding installation, I can't help you because I am not using IIT Guwahati's license. I am using my IIT Bombay's license. So I guess you will have to write to them. IIT Guwahati, maybe NPTEL team or professor or their course TA.
Okay, sir.
can I
Okay, did
reset and
Sir,
you?
where
run
is
again?
reset button?
Yeah, here,
It's
here.
here.
So that reset button from your mouse cursor. Yeah. Or here also it's written below there. Near to dynamics, it's written reset. So you can also see there. Just reset it and then run it. It's a good practice to do. Just do it, Abhijit, and
Yes,
display
yes,
the
I will.
results. Okay, results available.
I have resetted and again run the simulation. Now
Yeah.
results are live.
It may not affect your results, but this is a good practice to do. First reset it and
Yes.
then simulate it. So see what is happening. Your all feed is converting into vapor, right? So what
Yes.
is this phenomena called? If you have learned this in your thermodynamics course, what is this phenomena called? Please someone respond. What is this
Bo-
temperature called? This is not 120 is not the
Condition.
exact temperature, but sorry.
Azeotropic condition.
No, not azeotropic condition. Azeotropic condition
boil,
is
boil,
when your y and x are same and you can't separate it
boiling.
at particular temperature. No. Yeah, boiling,
Boiling
but
point of
not
mixture is
Saturated
what
temperature?
which temperature?
reduces
Saturated temperature?
below 120 degrees Celsius.
No, that is one particular term that you have learned in thermodynamics. So this is called dew point temperature.
Okay.
I
Dew
guess
point.
you know bubble point and dew point. What is bubble
Yes.
point? First droplet of liquid is
Point.
converted into vapor. That is bubble point temperature. And dew point temperature is the last droplet is means it is all vapor now. That is dew point. So can we tell if I go for 130 degrees Celsius, will it will show vapor all in vapor phase, right? At 130 degrees
Yes.
Celsius also it will show. So how can we say that 120 or 130 what is our dew point? How can we say? How can we measure dew point if I want to measure the dew point?
When
There was
first.
an option in flash drum block. Can you go to flash drum block? I'll show
Yes.
it to
Yes.
you. I
Okay.
guess
I'm
this
there.
these parts are not covered by sir, but I'm I'm trying to show it to you. It will be useful.
Yes.
Yeah, go to flash.
I'm there in flash.
Wait. It's not visible yet to us. Just wait. Yeah. So we need to find the temperature at which our whole liquid is converting into vapor. So we will remove the temperature and we will go for vapor fraction and we will write vapor fraction as 1. So at what condition, at 1.5 atmospheric pressure, we are getting whole liquid converting into whole vapor and we need to know that temperature. So just go for that temperature part here and choose vapor fraction. We don't want to specify temperature. We want to find the temperature at which y is equal to 1 happening. Yeah, and write vapor fraction 1. Here, vapor fraction 1. Then reset your simulation and run it. So we will be getting exact temperature. I guess you have learned this bubble point, dew point. Am I correct or not?
Yes, yes, we have learned.
Yes, you guys have learned it. And we are just
Why have we
seeing.
why
Yes,
have we
yes.
given vapor fraction as 1?
Because we want to calculate dew point. What is the dew point? At which y is uh, when whole liquid is converting into whole vapor? What is that one temperature? 1.5 atmospheric pressure. At first, it is converting whole liquid into whole vapor. Initially, what we did in part B, we used 120 degrees Celsius temperature and we checked that whole liquid is in vapor. But we don't know if that is the temperature. It will be in whole vapor phase at 130 degrees Celsius also. So here we want to check at what temperature vapor friction is converting into one, and that temperature is called dew point temperature. Is it
For
done or
bubble
not?
point, we can keep it as a 0 and check it, right?
Yes, yes. So see what is the temperature? 118.17 degrees Celsius. So this is the
118.16.
yeah, this is the
Sir,
temperature.
it's the vapor fraction sum.
Sorry.
Sir, is it sir in when vapor fraction is equal to 1, it's the
Yeah,
sum of
that is
vapor fraction of benzene and toluene both
yes,
in
everything,
vapor.
everything. Yeah, yeah, everything, everything. It will be one summation one. No, not summation. Yeah, summation one. Everything will be in vapor phase. So you can see, just go to mole fraction option. See, it's everything is in vapor phase and summation is one, not individual. It can't be one. Individual summation can't be one. It will be 1 plus 1
Okay,
plus 1
okay,
3.
okay.
That is not right. So this is called dew point temperature. That is 118 degrees Celsius. So now you
118.
know what was the value. Can you again have 118.167 degrees Celsius? This is your dew point. Can anyone tell me how can we calculate bubble point and dew point mathematically? Those are formulas if you remember in chapter 11 or 12 of
Yes.
Yes.
Smith, Warnes and Abbott.
Antony equation.
And
No,
vapor.
Antony equation is for saturation pressure calculation. What is the equation for bubble point? What is how
Sir, Raoult's law with activity coefficient.
activity coefficient is fine. We are here assuming ideal conditions, so activity coefficient is fine. Okay, I'll tell. Bubble point pressure is calculated as x1 p1 set plus x2 p2 set, right? And dew point pressure is calculated as 1 upon y1 by p1 set plus y2 by p2 set. I will force all of you to see that chapter. I don't remember is it is 11 or 12. You should see this bubble point and dew point calculation how it is performed. That is, if you want to
Okay, okay,
calculate
sir.
temperature, if you
Is
want to
equal to
calculate, yeah, if you want to calculate temperature is a iterative process. But if you want to calculate the pressure we can directly estimate. You want to
Yes.
calculate pressure at particular bubble point pressure at particular temperature, right?
Yes.
sir.
Uh,
Okay, we know that P is equal
yeah.
to x1 into P set plus x2 into P2 set, and
Yes.
here we put the x1, the mole fraction of feed. I
Yes.
thought so.
No, here we are calculating dew point, not bubble point. So it will be
Yes,
1 upon y1 by p1 set plus y2 by p2 set.
yes, yes,
This
yes.
is dew point, not bubble point.
For
So
bubble
what do
point
you,
calculation,
okay, so
I say.
wait, I will tell you how we will proceed. Your equation is P is equal to, okay, I'm sorry, I don't know how to write it, or I can, is it required to show the equation from book or is it fine?
Can I open soft copy of book?
I have, okay, you open it. Okay, you open it. It is simply
Or
one upon,
if you want, you can also open the.
okay, you can stop sharing. Actually, this problem is anyway over. So you can stop sharing.
Yeah, thank you. Thank you.
You can stop sharing.
I have.
Wait, we will just open it. Just give me a minute. I will share my screen and show it to you. Hemodynamics, this Smith. Which books you are following?
Van Ness and Sandler.
Smith and Vani.
Okay, Sandler is also good book. I learned from Smith and Varnes during my BTech. So, which is the chapter? Chapter 12. Yes. Yeah, see here. Wait, I will now share my screen and it will be visible to all of you. Share screen. Can you see? Yeah, so see, this is the dew point temperature, that is 1 upon y1 by p1 set plus y2 by p2 set. So here what we have fixed? We have fixed the pressure of drum. So P will be 1.5, right? Hello?
Yes, yes, yes.
Yes,
We
sir.
are.
P will be 1.5 and P1 set P1 set is basically based on Antony equation, that is A minus B by T plus C, right? And we want to find the temperature. So what we will be doing, we will first assume some temperature. Let's say I am assuming first 100 and it was 110. So let's say we are assuming 120 degrees Celsius. I will put 120 degrees Celsius in Antony equation. I will measure P set and put this value y1 by p1 set plus y2 by p2 set. If this value P is equal to 1 upon this value is equal to our 1.5 atmospheric pressure, then temperature is correct. If it is not meeting the requirement, then we need to go for some other temperature. This is the iterative process. That
And sir,
I
Y1
guess
and Y2 are the feed composition, no?
yes, 0.6, 0.4, 0.6, 0.3, 0.1. So this is at least what we did in our exams. I don't know how you used to solve. Okay, so I guess bubble point and dew point concept is clear to everyone. And
Yes.
how can we calculate? I know I'm giving you to solve a bit difficult problems because sir has not solved, sir has not given this kind of it's difficult problem. But if it's not fine for you, then let me know. I will prepare some simple problem. Okay,
No, sir, it's
It's fine,
fine.
sir.
it's fine. Okay,
It
now
No,
requires
it's
we are
good.
tough
going.
questions.
Okay, now we are going for one more difficult problem than this. Most of you have learned TXY, PXY plots in distillation column. I guess you have learned. Yes or
Yes,
no?
we have.
In thermodynamics
Yes, sir.
also you have learned. So we will plot one TXY, PXY plot and XY diagram. XY diagram you all have used in distillation column in some McCabe-Thiele method or Poncon-Savary method. You need that equilibrium diagram XY. So we will generate it. So, okay, I will solve this problem. It will be difficult a bit for you. I need to show you how to do it. So, um, problem 3. Okay, I have already solved it, so I will just show you the steps how to do it. Or do you want me to solve it again? I can do it if you want to.
If you solve that, it will
Please
be.
start it.
Okay, I will solve it then. Wait, let I first need to figure this out, this admit thing, because people are joining very late. This is not good. Mm, just bear with me and my laptop. Yeah. Okay. We will do it. New simulation I am choosing. Yes, I want to close the current simulation. Okay, so what is the conditions? A binary mixture consisting of 60 mole percent ethanol and 40 mole percent water is introduced into a flash chamber with a mole flow rate of 120 kilomoles per hour at 3 bar and 25 degrees Celsius. Okay, use the Wilson activity coefficient model as a property method. Okay, I would like to first stop. Can we use ideal model here? We can't use ideal model here, right? Because ethanol water, that is not a ideal solution. So we are using as a we can go for many other property methods like NRTL methods, unified method. Here we are using Wilson activity coefficient model. So what is Wilson activity coefficient model? This Raoult's law is basic. Phi into P into phi is equal to X gamma P set. So phi, we will be assuming Wilson, this model assumes phi equal to 1. That means our vapor phase is ideal. So we just need to deal with gamma. So these are the gamma equations, ln gamma 1 and ln gamma 2. These terms lambda 1 2 and lambda 2 1, those are interaction parameters, because ethanol and water, those do have, they have some interactions between them. That's why this gamma 1 2 and gamma 2 1 we need to add. So you can see how complex this equation is. And if we, this is just for two components, x1 and x2. If we have three components, you can imagine complexity of the equation, that too just with Wilson equation. So let's start our problem. Sorry. Okay. So it is 60 mole percent. Let's first add our components ethanol and water. Ethanol, water. I'm directly adding it. Now I'll go to next. I will choose Wilson. Wilson won't be available here. That is not a base method. Our method name is Wilson. Wilson will be at the end W. And the base method is, then it will take Wilson. Okay. So we need to add Wilson property method. Now, okay, wait. I forgot to show you something. Okay. Properties. I am going to next. So this is showing interaction parameters, right? Aij, AJI, Bij, Bji. These are interaction parameters between ethanol, water, ethanol, water. So we just don't need to change anything here. So we will just press next and we will go for, we'll go
Estimating
to
using unified.
no, we don't want to do
Estimating.
that. We don't want to do that.
Oh,
That is
why?
not important. That is
Why?
not important for now. That for calculating interaction parameter, it uses some different method. That is not important for us now. Someone is not muted. Okay, that is not important for us right now. So what we need to do, we need to go for a separator, flash drum. Everyone can see, right?
Yes, we can.
We have top, bottom. This is feed. This is top. This is bottom. You can do these things if you want to. These are not mandatory, but this is a good practice to do. Now I will be adding feed flow rate. What is feed flow rate given to us? 120 kilomoles per hour, 3 bar and 25 degrees Celsius. Okay. Sorry, I forgot. 120 kilomoles per hour, 3 bar. What was the preset? 25 degrees Celsius, right?
25.
25 degrees Celsius. And our composition is 60 mole percent.
60 and 40.
So first change from mole flow to mole fraction, 60 and 40. Okay. Now what we want to do, let's say if we are going for directly flash drum, what we need to enter, we need to enter temperature and pressure, correct? Hello, correct?
Yes, sir.
Yes,
Yes, yes.
but what we are willing to do, we are willing to develop TXY diagram at 1.01325 atmospheric pressure. I guess pressure is 1.013 bar pressure. So one way what we can do, we can change our temperature every time with that pressure and we can plot that diagram, right? But we don't want to do that. We have already software. So what we will do, just see here carefully. We will first go to properties. After doing this, we will go to properties. Then we will click on this analysis. Okay. Then we'll choose binary. Why we'll choose binary? Because we have ethanol and water. So we'll choose binary. It will show. Okay. Now, what we want to do, our pressure is 1.01325 bar, correct? And I am taking 0 to in 0 to 1 in mole fraction, I'm taking 50 points. So let's first run this and see what happens. I'll just run it. Okay, I had to choose this run analysis. Don't show the plot, I guess. It will take time. Okay, I will choose this run analysis. Okay, so you can see we have 0 to 1, 50 points. And this is for each composition. We have this TXY plot. This X, this what is this curve called? This is called bubble curve, and this is called dew curve, right? Because this is in liquid phase, it is about to convert into vapor, and this is already in completely vapor phase, right? So I guess you have seen
Yes.
this diagram, TXY.
Yes,
You can
yes,
play
sir.
with some parameters, like you can change the temperature scale from Celsius to Kelvin based on your requirement. Okay, this is clear how we did it.
Okay, sir.
Okay,
Yes,
so
sir.
now next what I want to do, I also want to add XY plot. So I will just add XY plot. Choose that and did you follow or not? All of you? How did I do? Okay, I will show it again. Uh, from analysis only, we have already TXY analysis. So for this analysis only, we want to plot XY. So we'll just choose XY. So see, you can see XY, mole fraction of ethanol in liquid phase versus vapor phase. So this is used in distillation. You have developed, you have used, you in our time, we were given questions to find number of trays using McCabe-Thiele method. So we were given this XY equilibrium data. So this is XY equilibrium data that we generated using our bubble point dew point concept that we learned. Correct?
Yes, sir.
Okay. So I guess this is clear. Now I want to plot a PXY plot. So it is PXY plot will be at constant temperature. So how will we change the temperature? Can anyone? I am just going here to simulation, and can anyone tell me the path how to do it? Okay, I will first reset everything on the safer side. Okay, can anyone tell me how will I first proceed for PXY diagram? What we did in TXY diagram? We
We
Move
fix
first,
the
So for
pressure. So in here we fix the temperature.
yeah, we will fix the temperature in same way. What did I do? Can anyone tell me, or does anyone want to note down the steps? Okay, first we went to the properties option here. In property database we went, then we choose this binary. Or which if this is not directly available, then you need to first choose analysis, then binary. Okay, so I'm choosing binary. Okay, now what I want to do, I want to plot PXY plot. So I will choose from analysis type TXY to I will choose PXY. So here automatically temperature will be changed. And our temperature is, I guess it's 90 degrees Celsius. It is asked at 90 degrees Celsius. Yeah, it is 90 degrees Celsius. So I will add 90 degrees Celsius and I will just simply run analysis. So we have PXY plot, correct? It is the same method. And this plot is at constant temperature. And now I want to plot XY diagram for this temperature pressure condition. So what will I do? I will just choose XY plot. And it will show me XY plot. Is it somewhat similar to what you learned in this is not ethanol, XY plot of ethanol? Does this look like this only or not? At high concentration, it will follow up this line. If you remember, it was like this only.
Yes,
You
sir.
can check your whatever book you follow,
Non-ideal.
either Trebal or DK Datta. You can see, I guess it is given XY plot of ethanol water. Okay, so I guess it is clear to everyone. You can play with these parameters. Now, one more thing I want to show, but I am not sure if it will work or not because I have not tried. But let's try here only. Okay, we know that ethanol water forms azeotrope, right? Does anyone know the azeotropic conditions?
Yes.
What is the condition?
97% ethanol, I thought so.
97 what percent? Weight percent,
96
mole percent?
mole fraction.
No, that is weight fraction. 96 fraction ethanol and 4 weight fraction water. And if we convert it into mole fraction, it is around 87. I'm not sure what is the value, 87 and 13 mole fraction. So let's try with azeotrope search. I want to search azeotrope is forming or not. So I will choose this ethanol water. Choose it is not complete. Why it's not complete? Okay, I need to give some temperature here. Some conditions I just need to give. I will just give it. Because this is different energy. I can give some 110. I'm just giving it in 1 bar. Okay. So for this, I want to search. Yeah, increasing this views again. Okay. So I want to search azeotrope. So first, at any condition, we are just seeing. Now we'll do azeotrope search. Oh, it's not working. First, we need to run. No, it's so see 78 degrees Celsius. Can anyone check on Google what is the azeotropic condition?
How
Wait,
did
I
you
will
reach
only
here?
wait. I will only show it to you. Wait. I will be there. Just give me a minute. Oh, I am not able to access. I don't know how to minimize it. Okay, I don't know how to minimize. Can anyone check on Google what is azeotropic condition? Yeah. I can see. Now azeotropic condition. So someone has asked me how did we reach there. I will again show you. Azeotropic condition for ethanol water. What is that condition? 95.635 of ethanol and 4.375 of water by weight. And that is 78.4 degrees Celsius. So here what are we getting? 77.9, 78 degrees Celsius we are getting. And this is mole fraction. We can change it here from mass fraction. So it is 94.6 and 0.054. Okay. So we are not getting accurate results, but we are getting somewhat very near. So this accuracy will depend on what kind of model we are using. So this will affect here. This will affect on TXY plot. This will affect on XY plot. This is correct on this is clear or not to everyone?
Yes,
I
sir.
will
Can you
again.
repeat the step? How
I
can
will
I find
again.
it?
Okay. So just enter some conditions, pressure and temperature in flash drum. Then go to this azeotrope search option. Wait, I need to reset. Wait, I will reset it. Okay. I will go for azeotrope search option. Why it failed to launch? I don't know. I will first run it.
Run.
Okay. I need to first run it. Okay. First add some conditions and run it. Now go for azeotrope. Oh no, there are some. I don't know now. It's not working. Azeotrope search has always issue. Okay, what should I do now? Can anyone share their screen and show it to you? Can show it to anyone, everyone? I can guide you. I will try one more time. If it works, it works. Azeotrope search is always a problem. It always doesn't work. Okay, results available. We can see. I'll try again. No, it's not working. So can anyone share their screen? I'll guide you how to do it.
Can I share?
Yeah, okay, you share. Today you are the volunteer. Oh, people are joining at 7:50 also. Okay.
Is it
Now,
visible?
yeah, it is visible. Now go to home. Oh, no, you need to set up the problem again, right? It
Mhm.
will take time.
Yeah.
Okay, just keep this question. Go to no, don't do anything. Just go to that problem. Press this back. Yeah. Now, go to home tab. I guess you can see next to file tab, home. Yeah. Now click on Azure Drop Search. I will just show you how to do it. Azure Drop Search. Search Azure. Click on Azure Drop Search.
It's not
It's
responding.
taking. Yeah, it will
Hmm.
take time. It is this bit painful. It's not working.
It's not responding.
Okay, then what I will do next time, I will maybe prepare some screenshots for this, or I will try again. Wait, I have one more file. Let me see if it
I will
works on.
stop.
Sorry.
I will stop sharing.
Okay. Wait, I will open my actual file where I don't know if it work or not. We will try once. Can you see my screen? Yeah, you can see. It is problem number 3. Don't worry, there are only 3 problems for today. 4, 5, 6 we will do next time. Okay. Let this window. Okay, so what I will do first, I will go to simulation. This is the same problem. I have set up everything. I will enter some conditions. Let's say 100 degrees Celsius and 1 bar. Now I will run my, I guess it will work from here only. Yeah, Azure Drop Search. Just choose the components, name what ethanol water, then go to this Azure Drop part. Oh yeah, it's showing. Is it clear to everyone what I did?
Yes, it's
Yes, sir.
clear.
You can
Where did you
change
change
mole.
the units?
Yeah, here mole to mass. So you can see
Okay.
94.6 weight percent. And if you go for some different property model, maybe it will give you some a bit more accurate results close to experiment value. Wilson model may not be working properly for ethanol water. So you need to go for some high degree models, NRTL or something else. Okay. So I will stop this. Is it clear to everyone? Yes.
Yes, sir.
Yes. Yes.
Yes, sir.
Yes,
Okay.
yes.
So let's.
And
I
one more thing. Do you have any tabulation something like for which liquids for which
No, we
uh,
can't. We can't find even those kind of table. That is based on some like NRTL model is non-random to liquid theory model. So it is, I have written, Wilson is used for similar size molecules. And NRTL is used for more complex binary and multi-component mixes. So ethanol and water, they are obviously not a similar size molecules, right? So it will not perform the way it should perform. Wilson activity coefficient model, it won't perform the way it should perform, right?
no, no, I was just asking, do you have any
No,
uh,
no. I don't have anything.
recommendation or a tabulation, something like for which systems we choose
No,
which
at least I don't
models?
have right now. I will try to prepare for next time.
Okay, thank you, thank you. If you do it, it would be of great help then.
But it's not generally like for this system you should do this. As for my currently I am working on one levulinic acid water system. So we go for best and Unifac is always best. It's always best to go for Unifac model. So these models are, see, this Wilson coefficient model, if you can see, these are the terms. If we go for higher degree of models like unique model, unifac model, these won't be this easy. Ln gamma 1, ln gamma 2 calculation. There will be many other calculations involved to estimate gamma. So that increases your computational power. So it is somewhere between your computational power and your accuracy. But I always go for unified model because it is always best and it will give you best results only. Okay, so this problem is also clear. TXY, PXY plots, and so what we did today, we just simulated one simple flash drum problem. Then in second problem, what we did, we saw that flashing is not happening because temperature is also low and pressure is also same. Then we increase the temperature pressure condition and we saw that everything is converting into vapor phase. So that is called dew point. So we learned bubble point and dew point concept, and that concept we used for developing TXY and PXY plots. Okay. So now some small questions. I guess you are having assignments of this kind of questions. So I have prepared. What is Aspen? Full form of Aspen? Anyone?
Advanced system.
For process engineering. Okay, the full form I have not written here, but you know, advanced system for process engineering. That is the full form of Aspen Plus. Now, second question: Aspen Plus is available for which operating system?
Windows.
Window.
Windows.
We can't install it in Linux. Okay. Now, third, which approach is used for Aspen Plus simulations?
Secular.
Sorry, you
Sequence
are not
modular.
Sequential modulus.
sequential modular approach we are using. Correct. Now, the maximum number of characters that can be assigned for
8.
making a component ID is 8. Okay, these kind
8.
of questions no one asked, but your assignments may have these kind of questions, so I have prepared it. Now next, sorry, someone is saying something. Hello. Okay, the compounds can be searched on the basis of, on what basis we can search compounds?
Contains equal and
No, that is compound name, but other than compound name, what on what
Molecular
basis?
weight, boiling point.
Yeah,
PS
molecular
number.
weight.
Molecular weight,
Yeah,
boiling
correct.
point.
Molecular weight and boiling point. Now this question. So tell me, what is B1? First, tell me what is this B1 block? What is
Mixer.
this called?
Mixer.
mixer,
Mixer. Then B2 block.
heat exchanger,
Exchanger.
It is a heat exchanger. Then B3 block.
reactor,
Reactor. CSTR.
Continuous time reactor. Yeah. Fourth block. That is sorry B4.
Distillation.
distillation,
That is a displacement
Distillation.
valve. And B5. It's a pump.
pump.
Right.
Pump.
Pump.
Okay, now sorry, someone is. You need to mute yourself. Okay. Okay. Okay, what is Rawls law and when can we use that? Just tell me the equation of
Low
Rawls law.
low pressure, high temperature, non-interaction.
Okay. What is ideal Rawls law? That is Yp equal to X P set. And that is this
XP.
is non-ideal. So when can we use ideal Rawls law? Vapor phase is ideal and liquid phase
Vapor
is
liquid
ideal.
equilibrium.
No, not vapor liquid equilibrium. We are performing all these calculations for vapor liquid equilibrium only. This is ideal Rawls law. This is ideal Rawls law and this is modified Rawls law. So modified Rawls law, we have additional term of phi and gamma. Phi is for vapor phase that shows deviations from ideality in vapor phase, and gamma is deviations that are shown from ideality in liquid phase. So vapor phase is, trust me, vapor phase is not a big issue, but liquid phase, the non-ideality in liquid phase is very painful if you are going for some, if you are doing some higher simulation. So we can only use ideal Raoult's law when liquid and vapor both phase are ideal, and we know when liquid is ideal and when vapor is ideal. We know the conditions. Okay. Now in Aspen, okay, these questions who wants to answer. What is the color?
White circle.
Red color, red color.
No, not red color. It is complete. Red means you need to stop.
Oh, okay, okay.
It
Required
is
input
complete.
is complete.
In blue circle.
Okay, yeah, you need to just understand that symbol. I also don't remember those colors and all, but you should know that red means it is either it is incomplete, or if you have run the simulation, it will show some error. Then yellow means your simulation is over, but with some errors. And this blue means everything is correct. Okay, yeah, the next question, the symbol white cross in red circle means simulation is done, but with some
Incomplete.
error. Correct?
Yes.
Next. Okay. The flash block in Aspen Plus is used for, why are we using flash block?
equilibrium calculations.
What did we calculate? Sorry, you are not audible. Someone was saying
Vapor
something.
phase and liquid phases.
Vapor
Flash
liquid
condition.
phase composition. Yeah, those are equilibrium calculations.
Yes.
Now, next question. Which Aspen Plus model is best suited for simulating ideal gas mixtures?
Ideal.
This is very
Ideal.
simple. Ideal. This is very simple. It's
Ideal.
ideal. You can't use RK. Sorry, someone is saying Peng Robinson. Hello. Okay. I assume it is a mistake. Ideal only we can use for ideal gas mixer. We can use ideal. That is ideal Raoult's law. You just should not use anything blindly. You should know something behind that. Ideal means what is ideal? That is Raoult's law. Ideal Raoult's law. Then 12th question. The prop keyword in Aspen Plus is used to select. What is it used for? Prop means property method. Simple.
Property method.
Specify a property.
Yeah, specify a property.
Specify
Now, sorry. Okay, I can't. Which type of block is used to represent a heat exchanger?
HX.
HX.
Yes.
HX. Yeah, correct. Now, next is which thermodynamic property is Aspen unable to calculate directly? Okay, I hope someone answers this.
Enthalpy.
Heat capacity.
Entropy.
Okay, let's
Entropy.
okay, let's see.
Entropy.
Okay, let's see. From here only, let's see. Why will it not can calculate enthalpy? We are in flash calculation. We estimated heat duty, and heat duty is difference in enthalpy of vapor and liquid stream. So it will obviously calculate enthalpy and heat capacity, right? Enthalpy is also from heat
Enthalpy
capacity.
is always calculated with reference.
I think
No
the answer
reference.
is
It will take
entropy.
0 or some any value. It will calculate enthalpy. What it will not calculate? Let's see.
Gibbs free energy.
Yeah, it will not calculate Gibbs free energy. Gibbs free energy is not something easy to calculate actually. Yeah, see. Enthalpy is there, right? You need to analyze what is there or not. This is molar enthalpy. Enthalpy you can calculate. Entropy also you can calculate. Heat capacity I can't see, but it is also there somewhere. Heat capacity is from enthalpy only, so you can also estimate heat capacity. So you can't find Gibbs free energy. Gibbs free energy is something not easy to calculate. That is a molecular formula maybe. So Gibbs free energy we can't calculate. Now next question, to specify a feed stream in Aspen Plus you would use the what option you will select? Stream option. Correct.
Stream.
Yeah, correct. Now next question, what are some limitations of using activity coefficient models like NRDL and Unifec? I am asking for limitations.
All the above.
No, not all the above. No, wherever it is all the above, the answer is not all the above.
Requirement for experimental data fitting.
No, this is the way that NRDL and Uniquec models are developed. So that is not the limitations. The limitation is we can't handle ionic liquids. Ionic species we can't handle with this NRDL and Uniquec models. Okay. Now, okay, this is very easy. Someone respond. What type of file extension?
BKP. Dot BKP.
Yeah, dot BKP. Next, what does the term flow sheet refer to in Aspen Plus?
Option B.
Simulation.
Diagram
A
representing
diagram
process flow.
representing process flow.
Yeah, that is what we did, right? Now next, what is the purpose of flash block in Aspen Plus? Why did we use
To
Aspen?
separate a mixture.
Option A.
Yeah, we separated mixer in 2 or more phases. It's a single stage operation, flash drum. Okay. Now next, what is the role of reactor block in Aspen Plus? Very simple.
Chemical reaction modeling.
Yeah, we are modeling chemical reaction using reactor block. Which unit operation in Aspen is used to separate components based on their boiling points? I mentioned this.
Distillation column.
Distillation.
Sorry, distillation column. Right. Now, what is the purpose of splitter unit operation in Aspen Plus?
Divide process stream into
B.
four modes.
Option B.
Into two or four
Divide more streams, correct? Splitter we will see in next class. Sir has covered in week 2 splitter mixtures, then distillation columns, then extraction unit also and heat exchanger unit also. Next week you are going to solve so many problems. If I am able to prepare. Then this question, which type of thermodynamic model is commonly used in Aspen Plus for chemical equilibrium calculation?
Raoult's law.
Raoult's law.
Why it's not ideal gas law? We use somewhere ideal, right? So why it's not ideal gas?
Ideal gas law
Sorry?
is different.
Yeah, ideal
Ideal
gas law is different. Exactly. Ideal gas law is different, and that ideal word that is written in property method, those two terms are different. Ideal is Raoult's law. Answer is Raoult's law. Nice, you are paying attention. Now, what is the purpose of block in Aspen glass?
C.
To represent a unit operation of piece of equipment, correct? We used flash as a block, and that is representing a unit operation, right?
Yes.
Now, maybe last question. Which of the following? I'm sorry, just a minute. Someone is trying to join at the end. Okay. What is the which of the following unit can be modeled in Aspen Glass?
Heat exchanger.
Computer programming.
Sorry,
heat
No,
it is
no,
exchanger.
asked.
option B.
Heat
Yeah,
exchanger.
Heat
mass
exchanger.
Unit
spectroscopy.
operation heat exchanger.
Heat
Mass
exchanger.
Heat ex.
yeah. Mass spectroscopy we can't do with Aspen Plus. Computer programming we don't need to do with Aspen Plus. A nuclear reactor it's not easy thing to just model with Aspen Plus. So this is all about today. If anyone are having any
Prasil,
questions, feel free
Prasil,
to ask right now. Yes.
at the start of the session, you mentioned that there was a YouTube channel which you upload the
I will upload
video.
after this video is over. I will upload.
No, no, no. Is there any corresponding channel? Like you have any personal channel?
You can search on this is first time I am doing this kind of session. So I guess you can search my name Prasil Kapadia NPTL. So it may show. I guess it will
Okay,
show.
Prasil NPTL. Okay, okay. Okay, thank you, Prasil.
Just search something. I am not sure how will it work or not.
In middle of the session, I tried to search and I did not get the result.
No,
I'll
because
try it again.
no, you will not get because currently the video we are just recording it. After recording is
No, no,
complete, I
no.
will upload there.
Is there any
Channel you are
previous?
searching.
Is there any previous
No.
videos
This
which you
is
have?
this is my first lecture. This is my
Oh,
first lecture.
it's very good. Yeah.
I have a question. Means I have a confusion. Like, what is the good practice to save the Aspen plus file? Like, it's a .bkp file or APZW file.
No, it doesn't matter. You should save BKP file. This doesn't matter. These are very small things. This doesn't matter. It automatically saves BKP files, and it had some. I don't remember those conditions. Sir has already told in sessions that I guess BKP file it saves files plus some backup data also in some different language format. I
Yes,
don't remember what it is, but
yes,
it is
yes, right,
something
right.
like that.
Yes. Got
Anyone want to
Mr.
ask anything?
Prasil, what about yesterday's lecture? I think I missed it. Is it
Okay,
also available in YouTube?
yesterday lecture I was not yesterday lecture was
Okay.
taken by Amit Sharma, so I don't know what he taught or how he
Okay.
is going to upload. I don't have any clue about that.
I have a question. Means regarding there are two sessions. So is it necessary to attend both the sessions, or it will be different thing in
Okay,
both the sessions?
I can't comment on something like this. It's up to you. Whatever you find comfortable, easy, time convenient, easy to understand, easy to follow, you can go there. I'm not supposed to comment on anything like this.
Prasil, can
No,
you
no, no,
show
no.
me?
My question is that my
Prasil,
question is
Wait.
Prasil.
One by one, one by one.
Can
Abhijit is
can
already
you?
saying something. Wait. Abhijit is already saying something. Let
let
him
let
finish.
let let, let him finish.
Yeah.
Rasil, can you show me the YouTube channel and the screen sharing so that I can type the exact words here?
Wait, I guess YouTube. I have not prepared it yet, yaar. Oh no, no, not from here. Wait, wait, wait. I guess this is my. Where can I search my YouTube channel? Okay, you will see Tarak Mehta Ka Ulta Chashma on my feed stream. Yeah, this is my channel, but it is empty currently. You can search my name, or this is the ID by which you can search. I don't know actually.
Okay, thank you.
Can I, sir, ask you one question
Yeah, please.
regarding gate examination?
Which examination?
Gate, sir, gate.
Okay, ask.
Sir, how you prepare during your undergrad program for
Okay,
gate?
so I will tell you everything. I first attempted for GATE in 2019. At that time, they used to just ask MCQ questions and those one, what it is called, just type one number, numerical type. I don't know what is the type
So yes,
called.
sir. Teacher.
Yeah, 2019 and 2020, I just appeared two times and then I have not appeared. But during my time, I prepared like I first of all, I had not opted for any coaching. I did by my own. Uh, I'm from NIT Surat, so there they used to teach everything very well properly. So I chose not to go there. So during my BTech, first I attempted for GATE. So at that time I could not clear, but I had given efforts, so it didn't. It was not in waste everything. So I appeared for second time during my job. Same way I was preparing and I cleared at that time. So what you were asking? Sorry, I can't see
Sir,
you. I
sir,
can.
are you referring any YouTube channel or recommend
No,
me?
no, 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 no. I will not lie anything. I did not. I just studied by my own everything. So I just I took some what it is called those gate series, test series or something. I don't even remember the names, but at that time I took one and I used to give two tests or three tests a day. No, sorry, one test in 2 days or 3 days like that. I used to give. Take test series like have some. Its gate paper is of 3 hours, right? Still it's 3 hours. So just try to in your mind prepare your mind to complete in 2 hours 30 minutes. So if you are able to finish your test series in 2 hours 30 minutes, then you will be able to finish your actual paper in 3 hours.
Sir,
Yes, sir.
the
Rasil, can
Slowly. One by
Rasil,
one,
can
please.
you spell your
can I
name?
speak?
Okay, who is saying? You mutually decide. We'll see. Okay, Abhijit, you tell first. After that, yeah, ask Abhijit.
I forgot. I was asking that means my question is that there are two sessions, like one is taken by you and one is from by Amit sir, right?
Yes.
So means
Hmm.
both the session content will be same or
No. I don't. I initially told only I don't know what he's teaching or how he's
okay.
preparing. I don't have any idea. I am just preparing
Oh,
everything by my own. Maybe he is doing everything by his own. So you can choose or you can attend both. It's up to you. I won't interfere.
yeah. Got it,
That's
got
why
it.
I asked
Please,
that's why I asked in the
And
starting if someone attended yesterday's meeting or not. If someone attended, okay, leave it. What were you asking? Samhira? Am I pronouncing your name correctly?
Please, I have a
yes, sir.
question.
I'm asking when you are taking another class
Every
because you.
Monday, same time, every Monday, 6 to 8.
Okay. Thank you so much.
Every Monday, 6 to 8.
Rasil,
Yes.
Rasil, can you spell your name? I'm not getting the channel.
Okay, you can see this. See, I will upload this is Prasil
Copy
Kapadian's
link and
channel and
send it chat box.
okay. I don't know it will work or not, but I will. Uh, Teams. Chat box is here. Okay, it is done. Can you see? I don't know. Wait, I will also check.
Yes, we can see. We can see.
Okay, so I guess whenever I will
Fasil,
upload, you can
ca-
see the
can I ask
videos.
a question?
Yeah, please go ahead.
Because I'm not a chemical engineer, I'm a
Okay,
chemist. Okay,
okay.
the Aspen Plus software is completely new to me. So, what
Yes, yes, yes.
basics I need to learn? But I need to learn the software to do my research work further. Okay, what basics I need to learn before start working with the Aspen
See,
Plus?
see,
How can I
there are
learn?
there are two ways. The first way is you can use it like a black box that I will not recommend. Use if you are using a flash drum, you should know what is flash drum doing and how it is simulating, how
Yeah,
equations are being solved. You should know
because
this thing.
yes, because some terms it's completely new to me. Okay, so I couldn't understand, but I need to
Okay.
learn everything. So how
So
can I learn?
so this is okay, I will tell you the fact. This Aspen Plus, the one that I am going to teach you, that is whole base of chemical engineering. Like in our BTech, we used to learn it in final year, final semester, because if you know everything about chemical engineering, then you can go for Aspen Plus. But for this, for you, I will suggest whatever
Okay,
blocks you are doing, like you are going for flash operations, use some mass transfer operation books like BK Datta or Trebal to just have some basic idea what is flash operation, how does it work. Then if next time next Monday's lecture, we will be solving distillation column. So you should know what is distillation column. We will be using DSTW model. So what is that
mm,
shortcut method, Underwood Gilliland method? You should know that. No one is going to ask you, but you should know before using it. You can use it as a black box every time you can use it, but it is always good to know what you are doing.
yes, okay,
Today we learned that bubble point, dew point, temperature calculation. So that
yeah,
was in thermodynamics book of J.M. Smith, Introduction to Chemical Thermodynamics. So those concepts are, everything is connected. Like mass transfer is also connected, heat transfer is also connected, and
okay,
this thermodynamics is everywhere. You can't escape from thermodynamics. In our BTech duration, everyone was able to relate everything, like heat transfer we can see in plants, mass transfer we can see in plants. Where is thermodynamics useful?
oh,
Thermodynamics is base of everything. I guess you understand what we did today from that.
would you recommend a book to learn almost all the basics?
Thermodynamics, you can use this James Smith Introduction to Chemical Engineering Thermodynamics by James Smith. I can show you the cover photo if it's, yeah, it's there.
Oh,
This
thank you.
wait, page number one till work or not. I don't know. This book, Chemical Engineering Thermodynamics.
Okay,
Okay, people are using Sandler, but I don't know. For me, this book was always easy to understand.
okay,
James Smith, H.C. Barnes, and about. But it's a huge content. If you want to just learn, you can go for this chapter number 12.
12. Okay,
12, yeah, 12 you can go. This all Raoult's law, modified Raoult's law, then various activity coefficient model, those are there only.
okay.
This is unified model. Someone was asking, so I'll just show you how complex it is to calculate
Yeah, so
activity
because the
coefficient.
equation
See,
is completely
yeah,
complex
this
to
is
me to understand.
in unified model, it is combinatorial plus residual part. So combinatorial part is itself this and residual part is itself this. And these parts are already having their subparts. It is
Mm.
very complex to calculate compared to what we did with Wilson equation of state.
But
You
it's
can,
uh, because the Aspen Plus is calculating everything, right?
yeah, it is
Itself.
calculating everything, but you should know this basic. You should know what is behind it. You should know. I won't prefer to. I won't suggest you to remember equations, but I will tell if
Uh,
someone asks you unified model, what is unified
at
model,
least I know
then
the basics. Why I need to
yeah,
choose the
how it
method.
is how it is calculated. It is based on some group contribution methods. It considers combinatorial and residual part. And it this term you can see UJI, UII. Those are interaction terms. You should know
Okay.
these things. In this interaction term is dependent on temperature. This also you should know. If temperature it is quite obvious. If temperature if we change the temperature, interactions will also change, right? So these are
Yes.
interaction terms are temperature dependent terms. These basic things you should know. No one is going. We were supposed to solve this unified model, and we were supposed to write theories about unified model in exam. But I will prefer you should not. If you don't know equation, that is perfectly fine. Equations are always there in book, but you should know basics behind that.
Because that's the problem. Yes, this is the main thing, right? We need to choose the correct property method
Yeah, I
to
will
run
not
the
say
simulation.
something.
But I don't have any idea how we can choose the particular
I
property
will not
method
say
for
what
a
is
particular.
okay. I will not say what is correct or incorrect, but this models NRTL also you can see Unifag, Uniquag, VTPR. VTPR you will not find in this book. VTPR is some advanced level thing. If you see this, okay, I'll show it to you. In this equation of state,
How do
if you
you
can
know? How do you know? Through by experience, or is there any
no
uh,
VTPR
uh, for the
actually
particular process we
currently
need to choose the particular method?
currently I'm pursuing my research work on some phase equilibria diagram.
Okay.
So from my experience, I can see that VTPR equation of state is currently the best predicting near to what it should be.
Okay.
That is volume translated. So in the if you know this SRK, PR, RK equation of state, they don't have VC terms in equations, but that VTBR equation of state, it additionally takes VC term, that is critical volume. That's why it is called volume translated Pang Robinson. You should I will frankly say I don't know what is the VTBR equation, but you should know concept.
Okay.
So
Because sometimes
you can refer this chapter. I guess it was chapter 12. Chapter
okay,
12 you can read. At least you can, if you don't
I
read or
could
you
get
don't
some idea,
understand,
right?
yeah, you'll get some idea. That's what my point is. Okay, anyone
Okay.
else?
Thank you.
Or should we
Yes,
stop?
Yes,
sir. Hello, sir.
Yes,
very
say.
much. It's very nice lecture. Even though it's basics, it's very good. I'm
Thank
using
you.
Aspen Plan since more than 15 years.
More than?
And just would want,
More than,
I'm
sorry.
15 years.
Oh, more than 15 years. Great. That you have
Yeah, just
good
I want to
experience
see
than
what
me.
any new things you are teaching. Just it's really very good because we forgot all these equations. We know how to use it, but we don't know
Yes.
what is all these equations because I passed
Yes.
in gate 99 and
Oh,
with the work
so
in
I should
industry,
call
we
you
lost
sir.
all
You are
these.
senior. You are senior than me,
No,
and you have very good knowledge than me.
no, it's good that you are teaching from the basics, so that's why I want to refresh my thermodynamics. Same thing like we also studied the same book. Maybe it's the second edition or something, but we are showing eighth edition of
Okay.
Vanness and about, and it's
I
good
guess you
that
can
okay.
download this book. Yeah.
Yeah, we can get whatever we want here in the plant, so it's okay.
Yes.
So it's it's all the best for your PhD. Also, I also have
Thank you.
doctorate degree from National Institute of Singapore in advanced process control.
Oh,
Just I
great.
want to introduce. I am working in Saudi Arabia
Advanced
currently.
process control you're working with.
Yes, already
That
in my
is bit
PhD.
process control is a bit difficult thing. You're from NTU Singapore, you told it.
NUS Singapore.
Okay. Okay,
So
thank you
National
for
Institute of Singapore. Yeah, it's really good. I will attend your lectures and give you the feedback. And we have also Aspen version 14, but this very slow with this AI modeling and all. You guys
yes.
have experience in this AI modeling or still
No.
not
I
done?
will. No. I don't know. And I would frankly say I'm using this Aspen Plus after 2 years. In my
Oh,
last, I used Aspen in my MTech project. Then currently my work is not at
okay.
all and on Aspen. So I have not used Aspen at all. I'm seeing this Aspen like you only. If you are seeing this for first time, I am also seeing after 2 years for the first time.
Okay, because we are using Aspen many things like Aspen Utility Planner, Aspen HYSYS, and Aspen
Yeah, that
Aspen
may be
Dynamic.
based on that may be on based on your requirements. I have not used those
Yes, in the
many
plant.
parts. I have not used those
It's
many
good that
parts.
you are
Okay.
teaching all the basics. It's very good. Thank you very much.
Okay. Thank you.
So, hello, sir.
Who is this? I can't.
Hello, am I
Ah, yes,
audible?
yes. Yes, 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 you are audible.
Yes. This was my first lecture, sir, and it was
Okay,
very good.
okay.
And
Thank you.
if I
This was also my first
have
lecture.
any queries regarding this course, then to whom should I contact, sir?
Yeah, you can directly contact to sir also, but I don't know how frequently you will get the response. And if you want to contact me, you can send an email here. I'll try to respond as fast as possible because I'm also working, so I it may be delayed.
Thank you, sir.
Or if it is something big, we can address on some session also. It's fine.
Okay.
This is also my first lecture. If it's your first, this is also my first lecture.
Yes, sir. Yes.
Okay. So should we stop now or okay? I guess we should stop now.
Fine, sir. Okay. Thank
Okay,
you,
we
sir.
will
Thank you,
meet.
sir.
We'll meet on
Thank you very
next.
much for your lecture.
Thank you, thank you. We'll meet on next Monday. I hope this strength will be maintained throughout till April, I guess. This strength will be maintained.
There are some good books
Yes,
in
sir.
Aspen. Will upload in
Thank you.
the. I think who should I email? Because
I'm
there is no
sorry.
group blog or
Uh,
something.
Can we
I'm
create a
sorry.
WhatsApp for this?
Actually, I don't know any of this enrollers because as I am TA, I am not given access of anything. I am just supposed to send a
No,
link
no.
to and
I can share some books, not the PDF copies, just the names, title names. Some good books are there in the websites or something. So I can just share the names. Very
okay, you
good
are.
books on Aspen.
Could you
Yeah, yeah,
could you
yeah, yeah.
please
Please do it. Please do it. Yes. Actually, during my time, okay, I have stopped sharing my screen. I will show it. Okay, first let me stop this recording. Stop recording. Stop recording and transcription. Okay.